To be okay, good. Right, thanks Hossein and Jim and Kaden and organizers for inviting me. As I've been having a great time here. I play the role of a fortune teller today, so it won't be a regular talk as other people. So I try to actually make it, futuristic a little bit and see what my personal vision is. Of course, please, take it just what it is. It's just my personal vision of where the field is and where it's going. So I think I should begin with mentioning that in ultracold molecules, basically, I'm like ultracold molecule person. So ultracold molecules have, enjoyed a lot of attention in recent months, and of course, that's what Thijs told us about. It played a major role in this. It's an observation of BEC, of microwave shielded molecules, and chemistry, and all these coherent interactions. There's been reviews in Nature Physics on all aspects a few months ago. Really nice. So we can, kind of imagine three areas for ultracold molecules, which are collisions, chemistry, quantum information science, and metrology. One thing that ultracold molecules are really great at, and I'm not going to talk about at all, is probing BSM physics, which is unfortunate, but like this review is a great introduction into that. So, and it's a, I leave it at that. So, but I just want to address some open questions. Okay, so. What are some of the open questions? So Thijs talked about shielding and losses and mysteries. And I think the really general question is that now we enjoy a really high level of control of electrical atoms, like atom level control. Would that be ever possible with molecules? So that's a kind of a question that I'm really interested in, because for that, we have a much higher level of control of atoms. We don't have to shield them. We just let them collide and then just control their Feshbach resonances, and they're just there, right, for us. So it's not technically complicated. And the question is, of course, shielding works, and but in order to go beyond this stop sign, right, we need to understand what's going on. And I would like to wager that a lot of the interesting things that makes molecules unique are beyond this stop sign. Okay, so we have to make a stop. But we have to put the pedal to the metal eventually, and then we have to ideally go fast past that stop sign. So, and for that there is a lot of issues. Like for example, several groups have observed magnetic Feshbach resonances in ultracold molecular collisions and atom molecule collisions. Here, the first was the science paper, and then Wolfgang Ketterle's group. And these nice resonances. I mean, there's no idea. No one has any idea what these resonances are due to. So there's a very rich and nice spectrum, but rigorous coupled channel calculations that are so easy to do with atoms on my laptop. I can run all this spectrum in a millisecond pretty much nowadays, because there's a few channels. With molecules, we're looking at a quantum leap from 8 channels or 10 channels to a million channels pretty much, and then we cannot do it very quickly, and suddenly we're up against the wall, right? And so this wall is something that I find quite fascinating, because it holds the key to understanding these resonances, and also to understanding things like sticky collisions. This is a great review here. And more recently, here at Harvard, Conquen's group they have been working on potentially observing entanglement in ultracold reaction products. And now they have observed that actually coherence in ultracold collisions of KRB molecules is preserved. So it means that if you start them in a coherent kind of state, then in the end you observe a product that are also in a consistent with the prediction that coherence is conserved during the chemical reaction. So we need to, it would be nice to understand, can we use, for example, chemical reactions to produce entangled molecule pairs, right? That would be really cool if we can do that, because it's very hard to entangle something that is not interacting like K2 plus Rb2. There's no electric dipolar interaction. So we can potentially, this could be this unique feature of molecules that they enjoy that no other systems can provide you, right? But there are others. There is something beyond this. So this is very fascinating, as with all open problems. But I would say also for quantum science, the unique value proposition, we know this term from corporate world, right, from consulting. It means that when consultants come to your job place and they talk about unique value proposition, it's very scary, right? Because it means it means that pretty much things are not going very well, and we are trying to downsize. But it's also good to think about unique value proposition in the peaceful context, right? When what really distinguishes molecules, right? Because we have We have ultracold molecules for quantum information. They face competition from Rydberg atoms, superconducting qubits, trapped ions, and it's nice to delineate kind of what cold molecules have to offer that cannot be also offered by other systems. Like, for example, I would say leveraging molecular complexity is another word. So molecules are just complex. It means that, okay, so this picture I just took from Cadence chapter, and Wolze and Anna Maria Reyes, I really recommend if you want an introduction into ultracold molecules for quantum simulation. I really like this chapter. So, and in this chapter, like molecules are just two-level systems, right? But in reality, like this is the reality, right? So this is how the energy levels of actually KRB molecule looks like. There's 36 states in the ground rotational states, and there's 108 states in the reverse rotational excited states. How there's more than enough to choose from, of course, for qubits, right? You can choose anything, any two of those states, but you can also think about encoding it in high-dimensional spaces, and also, as Caden showed us, we can use rotational states to engineer synthetic dimensions, which is, like a degree of freedom that can be like a whole new degree of freedom, like a dimension that we can use for quantum simulation. So, but coming back to ultracold chemistry. Okay, these are the two topics I'm going to cover today. But ultracold chemistry is really interesting, right? So this is the guiding question, and we have this gold standard of coupled channel calculations. They actually basically solve collision problem exactly. So they include short range and long range, and we have excellent potential energy surfaces, even for KRB dimers, even for trimers, even for 10 atomic molecules. But the problem is that the coupled channel dynamics, or quantum dynamics, cannot be solved on these surfaces. So, I mean, they have their own issues. They're not perfect, but they're reasonable, very high quality surfaces. But they're just sitting there because no one can do quantum dynamics on them, and no one is, not many groups are working on advancing methodology, right? So. Because these systems are very much beyond the gold standard coupled channel calculations, which means that we don't want to deal with this short range physics. We put a microwave shield here, and we still need this. I would like to kind of claim here, it's one of my major claims for this talk, is that we still need the gold standard, these coupled channel calculations, to explore what's beyond the stop sign, and things like new Feshbach resonances, process state distributions, entanglement generation, blah blah blah. All of those things are not available from microwave shielding calculations. So all these things are, potentially game-changing for the field of ultracold molecules. We need to solve the dynamics exactly. And so I propose, so there's some estimates. This is not going to be easy. It's very hard to simulate these dynamics. We have hundreds of rotational states, lots of states. I've shown you just KRB molecule, or the spaghettis, right? It's just like one KRB molecule, just two rotational states. Now you have hundreds. Imagine how many states they have there, like zillions. And there's two molecules gets multiplied, and then partial waves between them. You can easily get, actually, I've estimated for sodium-potassium collisions that Thijs mentioned, you need at the minimum of about 1 million channels, and the maximum we can do right now is about 20,000 channels. So there's like a factor of 50 there, and this scales effort scales like n cube. So it's a 50 cube. So it's almost like 1 million a factor. So we are very far. There's a very, very steep wall. So what do we do? So we can say, we cannot do anything. Let's microwave shield. But we can also try to develop more efficient methodology and try to break through this stop sign, okay? So try to understand what's really at short range. And this has been the focus on my own research for a long time. And I'm going to show my, feeble attempts to overcome these issues. So, we also, that's kind of not enough. I think also the issue is for the future especially, is that the experimental studies are currently done on typically alkali dimers. And for the reasons that, you can make alkali dimers and you can cool them, and so you can study their collisions. But, also experimental studies of other molecules, like light, chemically relevant molecules, they have also been performed. And there are groups working on this. But for those, so I think these are very highly valuable calculations or experiments, because for those molecules, you can actually solve quantum dynamics, including external fields. So this will tell us, and we will learn about a kind of toy models. You can think of these more complicated alkali metal collisions. And so as those experiments and efforts to cool these molecules actually progress going forward, more and more calculations and experiments would be available. So I would also like to emphasize that we need close collaboration between theory experiment and already hinted on by Thijs, but also for these molecules where we can actually do the calculations, very detailed close state-to-state comparisons enabled by also studies at Harvard by Kan Quenzny's group. We can now, thanks to her work, we can actually finally measure product state distributions in actually coincidence. So this is really a super important advance that will allow us to constrain potential energy surfaces and do quantum dynamics calculations even better. Okay, so these are all exciting developments, but also then once we understand the simple molecules, and I guess the underlying issue that we are trying to understand very complex systems without understanding simple systems first. So we don't have that. Like we need to build up in my opinion, from bottom up, like we can start from light to medium size and go to heavy molecules like KRB finally. This will be the pinnacle. But we're kind of starting with the pinnacle and saying, hey, we don't understand anything, but okay, because it's a very complicated system, so we need to probably pick up a simpler systems, like to begin with, right? So I'm not, of course, going to talk. This is vast, this is kind of a map with a lot of potential directions, right? But I just want to highlight here development of efficient coupled channel methodology in my talk, what we have been doing in Nevada, and also on close collaboration between theory experiment here at Harvard with Kwan Ni's group. So. And the stuff that I'm going to talk about today is ultracold RB plus KRB collisions, and with the kind of efficient basis set that we have been developing to minimize the computational effort in this already very computationally expensive calculation. So, some background, Kwan's group observed a hyperfine to rotational energy transfer. So in KRB plus RB collisions. So what happened is basically they created RB atoms in the excited hyperfine states and collided with ground state n equal to 0 KRB molecules. What happened is that KRB molecules got excited into rotational excited states, and then rubidium atoms dropped from hyperfine excited state to the ground hyperfine state of 1,1. And actually, it's quasi-resonant transition. So actually, the splitting between equal to 0 and 2 is 6 times approximately rotational constant of KRB, which is about 6 gigahertz, 6.8 gigahertz. So products were mostly observed in n equal to 2 state, and then 1 and 0 were populations in those states were much smaller. So okay, so this seems like not the kind of sticky collision system, although there's a lot of mysteries already associated with this, because previously Kwan's group observed the lifetime of the complex is 5 orders of magnitude longer than it should be, according to RRKM predictions and density of states calculations. 5 orders of magnitude is quite a big discrepancy, right? So, and so involving and studying the nuclear spins, and that calculations of RRKM, like nuclear spins were neglected, so maybe they could play a role here. So we actually set out, as my group, we set out to do full coupled channel calculations, and little did I know how complicated these calculations eventually ended up to being, right? So, but just to give you an idea, we really leave no stones, try to leave no stones unturned. So basically just include all the angular momenta that are in the system. So basically, in the atom molecule complex, like KRB plus K, if you try to do it exactly, there's 6 angular momenta, 6, okay? So I'll talk about 51 J symbols when you try to couple on this angular momenta. But so what is the best way to do the calculation? And the answer is there's no known way to do the calculation in this system, okay? So because all previous calculations just say, oh, let's just nuclear spins, let's leave them apart, okay? So they don't exist. But the thing is that the splittings due to nuclear spins are way larger than the collision energy and all the other, the collision energy is about like, about microkelvin, so which is much smaller than, so these energy scales are important. And of course, because people couldn't do it, they say they don't matter, but really the reason is it was very difficult to do. So we actually just included everything we knew about the system, and we collaborated with Michal Tomza group at Warsaw University, so he calculated for us some of the best calculations there of these hyperfine and isotropic, actually, Fermi contact couplings. It means basically all the spins interact. But, in addition to the common terms like potential energy surface spin independent, right? There's also spin dependent interactions that also depend on the distance, right? So, for example, the spin of rubidium atoms actually interacts with those spins inside KRB, and these interactions actually depend on R and theta, right? So all this, they're called like hyperfine, you can think of the hyperfine potential energy surface or something like that, hyperfine surface. And the thing is that like people haven't really included them in any calculation, so basically I had to just sit down and include all of that. But just some interesting fact, this is Michal's calculations on the potential energy surface and interactions in RB KRB. So you see that there's just typical, potential as a function of R. It's a two-dimensional. We did the rigid rotor calculation. So it was like fixed KRB distance. But you see, if you change the KRB plus between distance between RB and KRB, the potential, of course, change, different depending on the angle of approach, is pretty deep, about 1200 wave numbers. And the rotational constant of Kerr B is a fraction of a wave number. So you can imagine hundreds of rotational states get into this well and participate in the collision, which is actually exactly what happens. There's about 180 rotational states that is necessary for convergent calculations. So, but here, one interesting point is that you see there's a conical intersection actually that was identified in this calculation at short range. Conical intersection is pretty much like in this molecular thing where two potential energy surfaces come together and they touch like at one point, right? And then what happens is actually spin-dependent interactions, such as the spin-rotation interaction, which is like interaction of rotation of the overall collision complex with its spin, peaks like crazy. It's like there's a factor of 100 or more in this peak. So that actually gives you some food for thought, because like maybe these interactions actually are important, and you see these interactions are energetically accessible. So you collide in this even at very ultra-low energy, you're here. And so in principle, you can definitely access this region of conical intersection. So that what can happen is the spin interactions, they can scramble all the spins with rotational motion and maybe increase the effective density of states, increasing the lifetime of the complex, if we believe in our KM paradigm, which we should believe, because we know it tends to work pretty well for alkali dammers. So, you know, this could be a plausible mechanism. And so compared to there are also other spin-dependent interactions, such as Fermi contact, but you know, they are small compared to this peak, tiny peak. So what is actually quite intriguing, so we were able to, like I said, to do converged calculations, so we actually had to change the basis set for that, and then we have to invent with José Dencao a new basis set in order to make that happen, because like in normal basis set, you cannot get converged results. Rotation sets are just too many of them. So we basically found a fancy way, like theoretically kind of like a crazy way to couple angular momentum. You know, there's 6 angular momentum. There are many ways to couple those angular momentum. You can do like 2 pairs, you can do like 3 at a time, and you can do 4 at a time, whatever. There's like, you know, combinatorial ways, many ways. And turns out one way that hasn't been explored that we found that you know, works particularly well for the system is that when you couple rotational angular momentum and like, you know, put them away in a box, and then you decouple the nuclear spins. So all your nuclear spins come as tensor product part of the basis, right? When that happens, actually, you take advantage of the total angular momentum rotational symmetry of the problem, but actually you couple with the electron spin bath, right? So this would be a natural basis set for something like, you know, central spin model in condensed matter physics, where you have rotations that play the role of a spin, and then there's this little nuclear and electron spins that actually cause decoherence, right? Like in solid state quantum information processing based on electron spins, for example. You put a spin that's being like all these little spins are tugging on it and causing, like, you know, this decoherence that this can be actually explored. We're writing a paper on quantum simulation of central spin model with ultracold polar molecules, with rotations replacing the nuclear spins with Lincoln Carr. Actually, it was his idea. And this idea actually turns out really well, to work really well for collisions, surprisingly, right? Because like, okay, but why does it work for collision? Like, because these strongly anisotropic interactions, and this is too premature, so they actually couple. So this is approximately conserved. JR will play an important role. It's a total rotational angular momentum. It's not the total angular momentum. It's a total angular momentum minus all the nuclear spin angular momentum, okay? So an electron spin. It's just rotation, mechanical rotational angular momentum. So it turns out that this quantum number plays an important role in the whole business. So we set out to these calculations. We converged actually with 180 rotational states and 6,000 channels. This just gives you an example of, it's a small number of channels, but it takes a long time to solve this problem, because it's, you know, have to propagate those channels, and just like for 0 total rotational angular momentum. And this is kind of difficulties we're coming up. Remember those millions of channels that I mentioned, where like this is already pretty hard to do on a classical computer, but the maximum is about 20,000. So you can do j equal to 0, j equal to 1, but j equal to 2 already cannot be done. So here we are pushing there the limits of current coupled channel methodology. So, and the results are actually very strange. So we see this is a histogram of results. Basically, we also don't know really the potential energy surface very well. So we vary the potential energy surface a little bit. And then we actually, because we histogram the results. And what these results show is actually, if we assume that this total rotational angular momentum, or TRAM we called it, is conserved, then we don't get the theory actually peaks and always consistently predicts that the ground rotational state is populated in the experiment. So whereas this is really in disagreement with the experiment, because it should be skewed here and over here if weird match experiment. There are some outliers here. Actually, we examine these outliers. There are potential energy surfaces that give you, agreement with the experiment. They do exist, but these are unlikely. You see, most of the potential energy surfaces statistically are not going to give you reasonable agreement. And we haven't explored the entire potential, so this is just different potential energy surface. But pretty much, it's different from what is observed experimentally, and the reason for that can be suspected to be the lack of conservation of total rotational angular momentum. So when this is broken, this quantum number is assumed in these calculations don't agree, but if it's broken, the statistical model predicts that actually the ratio of populations observed experimentally. So which actually means that you can explain it by assuming that this is not conserved. But what interaction would break this total rotational angular momentum? Turns out it's really hard to break. So we think that that's what we stop, because we cannot do larger coupled channel calculations. But these calculations definitely show that the conical intersections and yes.
Sorry,
So
can you go back one?
yeah.
So you showed us now that you get this particular solution, but you also say, okay, you can actually get the right thing if it's not conserved. So, so what did you do differently for the?
So for not conserved, it's just statistical model just counting the states.
Oh,
so
okay.
because the statistical probability of just having n equal to 2 is 2n plus 1,
That
right?
seems a little bit disappointing that you do all this kind of complicated calculation and at the end that's exactly not what happened.
It is disappointing, but I think we kind of were able to rule, these things can be due to all the 6 angular momentum or conical momenta or conical intersections and vibrations. So we ruled out the 6 things and we narrowed it down to 2. So now we can claim, at least indirectly, that, that this is due to this interesting and notorious conical intersection dynamics at short range that is actually unique to molecules, that's causing this scrambling of total rotational angular momentum. This is this hypothesis that we put forward in this paper, which is now in the archive. So we now narrowed down, even though coupled channel calculations didn't really directly, allowed you to nail or to do a smoking gun kind of like demonstration of the, but still we learned from this experiment 2 things. First is that this is broken, likely, the total angular momentum, rotational angular momentum, and second, most importantly, these hyperfine interactions actually are strong enough at short range to change the dynamics. So at short range, they couple strongly to rotations, and that could cause the expansion of this Hilbert space. Like the nuclear spin or electron spin not conserved anymore, and so this lack of conservation causes this, proliferation of states. Yes?
So when you say that it's strong, what should I be comparing it to? The hyperfine splitting, the rotational splitting?
Strong meaning that it's causing non-near universal loss. So it's as strong as any other interaction at short range. So it's, hyperfine causes this. It was actually, so yeah, you should be comparing to hundreds of wave numbers. So at short range.
But it looks like if the spin orbit couplet or spin rotation coupling, it looks like this is only about a gigahertz or a few gigahertz.
Yes, and that is not enough to explain
Exactly.
it. So there is a mysterious, actually conicals, we didn't include this coupling at the rigid order level without varying the R, and we weren't able to break. So in order to break this tram, you need to go inflate it artificially by factor of 1,000, additional factor of 1,000, which means that these modes are, vibrational modes and conical intersections are likely to be extremely important, like dynamically, not just causing this spin rotation coupling that we can just tuck in this, effectively incorporate in coupled channel calculations. So it's still a mystery, but it's less of a mystery. So yes, Hussein.
You're suggesting perhaps that this breaking of this rotational symmetry is a consequence of this phase accumulation?
Conical intersection, this is what it does, yeah. So it's a complicated electronic coupling that also affects rotations, turns out. And there's this, because spin orbit coupling turns out to peak also at the conical intersection, there's this, and turns out it actually goes to infinity because they touch. So in the adiabatic Born-Oppenheimer pictures, increases without limit. So this is just the limit because we had to, cut it off somewhere. But also it becomes narrow and narrow and narrow as you approach conical intersection, and but turns out it has to be included in a rigorous way in order to make progress here. Yeah, but the underlying, we think, is conical intersection.
As you know, 20 years ago or so, there was a great hoopla about, including Berry's phase in these sort of reactive collisions
Yes.
that became buzzword.
Yes.
but in a way that's what
Yes, so I should mention, this is a good point, the groups of Brian Kendrick and Bala Krishnan and Svetlana Kotochigova, they did calculations here at short range, couple channel calculations. I think they finally converged them after 4 years of supercomputer calculations, and two postdocs participated in this, and so they did include conical intersections, but the problem is that it cannot include magnetic fields, hyperfine interactions, and something else. Oh, spin rotation interaction. So all the 6 angular momentum, out of all the 6, they only included 3, but they did include vibrations and conical. So it's kind of piecemeal picture. Now and the progress, I think that actually ties into the next topic that I'm going to say. What can we do to make it better, right? To make it more satisfying. So John Bone and others, there is a nice paper here. So they basically said MQDT is really interesting technique. So basically what we can do is we can use very complicated numerical supercomputer calculations here to generate these adiabatic curves, and then we can probably try and merge them with long range curves that we actually have from this theory that I've just explained to you. Because the nuclear spins are not important and short range also, we think. Well, they're not supposed, but maybe this picture is not, the adequate picture, but at least there is a way we can actually merge those calculations that Bala did with our calculations and apply a frame transformation here in order to, because the number of degrees of freedom is different, you have to add those 3 angular momenta at some point. So the way to do it is actually we developed in this recent paper that we published just earlier this year. So you can do this so-called MQDT with a frame transformation. Basically, it's just very technical, but you apply boundary conditions not with this regular K matrix, which is exact, but with this approximate K naught, which is the approximate K matrix, including only the raw vibrational degrees of freedom and conical intersections, let's say, but it doesn't have any angular momenta from the nuclear spins. And then you transform it into a larger Hilbert space using this rectangular matrix, right? You just expand it into a larger Hilbert space, and then it followed the standard MQDT approach, just calculating cross-section, and it wasn't clear that this works for molecules, actually. So we have demonstrated that it works very well, it turns out, for molecules. You can describe a couple channel calculations are in those symbols, and MQDT results are in lines. So this shows that, promisingly, you can actually do this, apply this procedure, at least to this MGNH. This is not KRB plus K, RB collisions, but at least there is some hope that we can save a lot along the way, 10,000, but perhaps more importantly, we just use different methods. We can use different methods in different regions. That's kind of the idea of MQDT. And so I think MQDT is a promising future direction for this, although I should also qualify my statement that we may not be able to do it, because if nuclear spins are coupled in a short range very strongly, MQDT assumptions break down, and only the full couple channel calculations, all 6 angular momenta will do, which will take a long time to do. So maybe we should go to simpler systems and explore some lighter alkalis like lithium. That has been some discussions in these directions too. So okay, so that's it for collision physics. Okay, so I'm moving on to ultracold molecules for quantum science, and I just want to mention a few things. I've been recently getting into this field, and I should say that, again, KRB is very complicated, but still very brave experimental groups here at Harvard, at Princeton. They're very bravely exploring entanglement with these molecules, and they were actually able to entangle molecules with pretty high fidelity, with more than 90% as far as I remember from those papers. And of course, this pioneering paper by Suzanne and Robin Cotte and Kate Kirby, but in this pioneering paper by DeMille really paved the way to all this amazing work. Okay, so I should say, I'm looking for new ways to kind of improve or build on this work, right? So what can we do? So, and I think really, like I said, unique value proposition is here because we are facing, all the molecules are facing competition, and the really important way in which molecules distinguish themselves is probing physics beyond the standard model. It has been shown that sensitivity to EDM and to other things like shift moment too, although I may be mistaken there, nuclear shift moment, is enhanced dramatically compared to all other systems, right? So if we can measure these splittings, and this is this picture from this very nice Nature Physics review, came out recently. So basically there's some new particle that is in beyond standard model physics that is actually supposed to lead to non-zero electron EDM. So the shape of the electron is no longer, spherical. And of course, there's amazing effort at GILA. There's amazing effort here at Harvard on measuring this GILA with molecular ions, here with neutral polyatomic molecules actually. So, and turns out that basically, like there's a huge internal electric field inside the molecule that causes polarization, and then if there is an EDM, which is not clear, it would cause a certain change in molecular energy levels, which is quite exotic, okay? So to measure it is not easy, so you have to be complicated sequences, right? But the point is that this is a great distinguishing feature of molecules, which I think is tremendously important. But let's say if we just leave this out, then what molecules have, what do they have to offer? Okay, they have to offer a huge, well-controlled internal Hilbert space, qubits, right? They also have rotational degrees of freedom, which is something amazing, because it seems like out of the entire universe, like of objects, like we only can have control of rotational degrees of freedom in molecules. We also have them in nuclei, but we do not necessarily have control over them, right? So the nuclei also rotate, and like larger objects also rotate, but molecules have this amazing control. Like Sam Cornish demonstrated coherence times recently exceeding 1 second between different rotational states. So you can do 1 billion quantum gates because the splittings between them, right, is about gigahertz, and you can keep them alive for about 1 second, right? So there's a lot of coherent operations you can do during the life. Rotational, I guess it was a second.
Rotational, the paper earlier this year was a second, but he's improved it in these recent results. I don't actually.
But nuclear spins, of course, you can do longer. I mean, it's like quantum, you can store. Right, so, but okay, rotations,
1.5 seconds in our paper.
you can think of them as qubits. 70 seconds. Well, but it's even better, right? I mean, you can do 70 billion operations. You can do a lot of single qubit gates. But importantly, of course, I mean, 2 qubit gates require dipolar interactions. And this is also a good thing about molecules. Rotational cells involved in these dipolar interactions. You can do gates in, I don't know, 10 milliseconds probably, or something like that for KRB. For sodium cesium, you can do it maybe in less than 1 millisecond. So you're still looking at more than 1 million 2 qubit gates during the coherent time. So this is also very impressive. But other systems like trapped ions, have even better numbers, as far as I know. So, like, what do we really gain here? And I think it's like, like technically, yes, it's very competitive almost already with trapped ions, but fundamentally, we also gain an enlarged Hilbert space with a lot of possibilities there, right? So, for example, this recent paper by Victor Albert and Michel Lemeshko and Li Liu looked at new kind of entanglement in in highly symmetric polyatomic molecules. They call it pararotational entanglement, which is basically a combination, as far as I understood it, this is a very highly mathematical paper, but it's kind of like a combination between rotational degrees of freedom and Bose-Fermi statistics. So basically, when you rotate a molecule, then it kind of goes onto itself. It's symmetric, right? So you have to do a factor space of SO3, basically, which is the full rotational group, or Lie group over, this Z2 or whatever symmetry group G of the point symmetry group of the diatomic of the molecule. Here it's like D infinite H, whatever. But this resulting factor space actually, has no analogs in physics. Or like read this paper, okay? So I just want to say that I think it has interesting topological properties, in other words, because it's a topological space, right? SO3. So when you factorize it, you get this multiply connected pieces of this topological space scattered around, which you can use to store in quantum information and do some quantum operations. Okay, so it's kind of like my take on this. But of course, Caden's paper on synthetic dimensions actually is related to that, although I'm not quite sure. Seems related, but I'm not quite sure what the relation is exactly. So someone has to figure that out. Because I think this rotational degree of freedom can be expanded in this spherical harmonics, and that's where kind of the connection can be. But okay, so I'm not going to go into that. But the thing is, really exciting new mathematical possibilities there, right, for molecules. But also in our group, we can kind of going in a slightly different directions, trying to use new qubit types and control knobs. For example, in this paper with Anna Maria Ray and Jun Yi, last year we thought about using spin rotational qubits, which is like not people like Suzanne used rotational states, and Simon Cornish uses nuclear spin states, but we said, well, we can actually look at different rotational and spin states in different rotational manifolds, like one state like that and one state with a different magnetic moment. It turns out very few people looked at that, And if you just derive the Hamiltonian, you get the Ising model. It turns out to be the Ising model, so you can generate things like cluster states and long-lived, you can think about using molecules for things like, measurement-based quantum computing, where you have these long-lived cluster states and nuclear spins sitting there for a long time, and you just measure different pieces, and then you do your quantum gates. But so, there's that, but also very recently, earlier this year, we had this strange mechanism, which we called ergodicity-assisted control, where molecules, they can get ergodic. It means that different, like for example, the Zeeman states, right, in the large magnetic field limit, they're kind of blue. Blue means like there's only one bare state contributing to this. So this is really technically this so-called inverse population ratio in quantum chaos theory, which is the sum of the fourth power of expansion coefficients. It basically tells you how ergodic state is, right? So if it's blue, it's very non-ergodic. So there's just one state, right? But if it's green, it means that there's a lot of different states contributing to that eigenstate. And that's very ergodic. And you see that at low magnetic fields, what happens? The nuclear electric quadrupole interaction, okay? That's another thing from molecules, right? You get these strange interactions that you never hear about other than in molecules, for molecules, right? So it basically causes the n, different rotational gamma momenta, to mix, different projections, to be more precise, of n, to mix in the n equal to 1 rotational manifold. And when you calculate the EDM between these, n equal to 0 and equal to 1, turns out that because of this coupling between different m sub n, the electric dipole moment depends on m sub n, not only on n, which is the rotational gamma momentum, but also on the projection. And it turns, importantly, for people who are, into quantum simulation with polar molecules, this is very important for, it uses to do spin echoes in these XXZ type experiments, because the sign of the electric dipole moment flips if you go from m sub n equal to 0 projection to 1. So by transferring molecules, okay, so you basically can reverse the dynamics and do spin echo experiments and beautiful things from these optical lattices of polar molecules. But here it's an extension of this, except that here you have like 10 different m sub n states contributing. And you may say, why 10? Because there's only 3, m sub n equal to plus, minus 1, and 0, but it turns out there's also all these projections of nuclear spin states that are involved. So basically the idea is that by coupling rotations to nuclear spin, you can actually control the electric properties of the molecule with an external magnetic field. And I gave a talk recently at American Chemical Society, and basically my teaser for chemists is basically you can make a molecule non-polar with a magnetic field, and they basically become very interesting suddenly and say that this is crazy because you cannot make its electric property of molecule. But you see here, by using interference between different states, and should be some bare states here in electric dipole, you can actually cancel out the electric dipole moment in a polar molecule by using these interactions with nuclear spins, involving nuclear spins. So this is a really peculiar mechanism specific to dipolar molecules. But I think it can be really interesting because a lot of people don't like electric fields for polar molecules because it's really hard to control electric fields, turns out. So you can use magnetic field to control electric properties. This is great, right? So you can tune, for example, electric dipolar interactions here. This is n value here is a transition dipole between 0 and 1. Yeah, the one that is most often used for. So basically, by all experiments before, you may be asking, why people haven't looked at that before, because okay, they were here in this blue region. There was no control because there was just one contribution from one bare state. There was no ergodicity, and so anyway, so you have to go to a smaller magnetic field, but it's not hard because it's not hard to generate 100 Gauss in the lab. It's much easier to generate, let's say, than 10 kilovolt per centimeter. So that's a mechanism that we use. You can actually use it to control dipolar interactions through the standard XXZ Hamiltonian. Like you see, there's this avoided crossings, which are like narrow resonances. They're similar to these level crossing resonances, Hanle effect, which is actually used to do magnetometry in atoms, in ultracold atoms. So now this Hanle effect kind of effect can be used to do also magnetometry because of this dB over, dJ over dB is very, very, very large. So if you're tuned near here, you're going to be very sensitive to external magnetic field, right? And so this is something that Anna Maria Ray actually taught me. So I was really, check out this paper. I mean, its sensitivity is pretty good. So anyway, and one other fundamental thing is that you can use these crossings to engineer qubits. For example, high-dimensional quantum simulation, so you could have something like a V system where the dipolar coupling is greater than the splitting between these qubit states. So you can no longer neglect the third state. You can actually involve actively these, if you are tuned to a right resonance or this crossing resonance, you can engineer a V system with molecules And dipolar Hamiltonian will have a new form. So there will be, of course, spin operators, but there will also be quadruple operators from the SU3 Lie group, right? Because like you know, usually we do SU2, and so we have SZ, SX, and Y, but when you go to SU3 and generally more higher, higher matrices, larger matrices, you get those operators that can be helpful, and because they go beyond the XXZ model, so you can use them for things like four-wave mixing and exotic squeezing and things like that. Okay, so lastly, I just want to say a few words. I have 5 minutes, Jim? Around 5 minutes? Okay, so that's plenty, right? And I already talked about it, so here in May, so I don't want to really, get too much of your attention, but I also kind of recently got excited when I mean, molecules are complex, okay? This is just kind of dictum and truism almost. Like everyone thinks that we need a quantum computer, and some people say it's a killer app for quantum computer molecules, mostly electronic structure, but also quantum dynamics is not less of a killer app, I think, because it's also exponentially hard with a number of degrees of freedom, but it has been getting more and more attention as of recently. So like this attention is, all these papers, like for example, Ivan Casal group, they mapped molecular Hamiltonian, like dynamics Hamiltonian onto trapped ions. And there's this Nature Chemistry paper, just actually back-to-back Nature Chemistry papers came out last year with also Kenneth Brown group here in Georgia, I think. He also mapped into trapped ions and simulated, and it worked. Conical intersections in 2 dimensions. It can be perfectly simulated with trapped ions, and also groups at Indiana, they looked at time evolution. So, and of course, this recent programmable quantum simulators that, this recent paper by Suzanne and Misha and Norman and Anna Krylov that really got me excited about this, because when I saw this Hamiltonian, I said, okay, this is something I can probably map my molecule onto, right? So, so you have single spins and then two spin-spin interaction and triple spin interaction, higher reactions. You can actually encode your molecular, if you can encode your molecular Hamiltonian in this form, you can start with a certain state and then propagate it, evolve it in time, like a wave packet in a way, right? Or you can trotterize it. It depends on, but no, you have to map it first and then you decide what to do with it. And then in the end, you read out the spectral function, and then from that you can determine energy levels and collision cross sections, reaction rates. And what is great is that this higher, I wasn't excited before because I thought people just can do binary and they cannot go beyond this, but this really got me hooked when I saw this term in Hamiltonian. So I decided, to contact my friends. So we have my former classmate, actually, Artur Izmailov from the University of Toronto. He has a group working on quantum simulation of electronic structure. He's an electronic structure theorist, but we found some common ways to interact, and we were able to discuss. For example, like if you have a Hamiltonian like this, which is a typically model reaction Hamiltonian, right? It actually describes things like isomerization. In this case, it's the reason why you see me actually is retinal molecule in your eye isomerizes from a cis form to a trans form, right? So it's a simplified Hamiltonian, of course, because it has one reaction coordinate and perpendicular modes to it. But turns out if we can map it into something like this, we can hope to simulate it on a programmable quantum simulator, right? And we already say something about it in this paper, but it's mostly unpublished. So this is the Hamiltonian. So this is just one unusual kind of high amplitude so-called reaction coordinate coupled to a lot of vibrational modes perpendicular to it. So, all right. So what we can do, we can just start with it, we can expand it around equilibrium, right? And then we can map just vibrations, we map into spins, and then single out this unusual reaction coordinate and deal with it, right? So how do we deal with it? Well, just expand it in Pauli matrices in a basis. We introduce a basis. It's not clear, I will show you in a second what kind of basis we use. And then, you have the matrix elements. And of course, like the matrix elements, let's say if you restrict your vibrational Hilbert space into 2 levels, so you get a spin 1/2. So you get this model, spin model, reaction spin model with product of spins and some effective magnetic field on the reaction coordinate. Those spins describe the reaction coordinate, these spins describe the vibrational modes. Okay, so, but the question is, okay, so how long is it practical really to expand this in? This is a complicated mode. How can we best expand it? And I think we found a way, since I was talking about here in May. Now this is the only new thing that I accomplished since that time. So you basically, you have this model Hamiltonian. We can do 4 qubits. and then we can use 16 space grid points. Okay, and then we can expand it in Pauli's. Turns out the number of Pauli's, even for 16 grid points, is quite enough for simple dynamics. No, maybe not for ultracold, but you can get, and turns out kinetic energy in this DVR basis is very sparse. So there's a limited number of X and Z terms and X and Y terms. So you can get away with about 60 terms for kinetic energy. But the beauty of that is actually potential is diagonal. So when you expand it in Pauli's, there's only commuting like I and Z terms. Right, so these terms are easier to simulate, and there's actually not a lot of these terms in the expansion. We don't really understand fully why. That is the case. We're kind of looking through this mathematical literature, how to expand these matrices best. But I think we found a really pretty expansion that we can now implement on a quantum computer, at least for this kind of simple model, 2D Hamiltonian. So I just want to conclude here by saying that there's a lot of interesting things with ultracold molecules, and I want to thank my amazing collaborators who did theoretical work, Paul Brammer, Mikkel Tomza and Kan Kwesny group on KKRB, RBKRB, Anna Maria Ray and my student Rebecca on the quantum simulation work, and thank you all for your attention.
A lot to unpack. Oh, one thing is we have to be back at 1:30 today instead of 2. So there'll be time to talk at lunch, but maybe you can take one question. Susanna.
So I love this kind of emerging kind of mixed eigenstates that involve this seems very elegant.
Very molecular. Yeah.
Very molecular, very elegant. So question is how realistic that is. So how much, how clean does your system have to be that you can actually take advantage of that?
You have to control magnetic field to such that the splitting is about 150 hertz. If the splitting, it depends on what you want to do. If you want to do these Q-treats, then you have to be very well controlled magnetic field because the splitting has to be less than 100 hertz. That's the strength, typical strength of KRB, let's say dipole. But in another molecule like sodium cesium, you don't have to be that precise because the dipole is going stronger, so the splitting can be larger. But if you just want to observe something like these level crossings, then I think they, in fact, they've already been seen in calculation. But the variation of dipoles hasn't been seen.
But that is, of course, I mean, your model is basically a kind of a single molecule model, and then, I mean, your upper paper there tries to put that into arrays where you get,
yes,
of course, all
exactly.
kind of extra stuff.
Yes, yes, but you can project the Hamiltonian for, so this is kind of like this Hamiltonian for Q-treats in interacting through dipole-dipole interaction. They have 256 terms. And for V system, most of these terms actually do not, drop out. And you get like very elegant, just 2 terms. But actually for the full system, it still remains to be derived. Yeah.
All right. Well, I guess we'll say thank you.
Thank you.
And, so back here at 1:30, lunch is in the same.